Good morning to people in the room and people online. Now, second day of the SU2 Developers and Users Conference. Our first speaker of the morning is Dr. Arne Voß from the Institute of CFD.
Okay, thank you very much, Raphael, for the introduction. Also, good morning from my side. I'm working at the Institute of Elasticity in Göttingen, Germany. And unlike some of the presentations we've seen yesterday, I don't consider myself as an SU2 developer. I'm more on the application side. And the application I have is an aircraft. In this case, it's called the DLR Future Fighter Demonstrator, which is an aircraft not designed by myself, but the preliminary design of that aircraft is done by my colleagues within the project. And the aircraft is specifically designed to be used as for research purpose and for publications. So the aircraft flies very fast with a design cruise Mach number of 2.0. It also flies very high, an altitude of up to 50,000 foot. And it's a very agile aircraft, which also leads to really high load factors in the range from -3 up to 9 G for the basic flight design mass. Just for those who are not so much into aircraft, to give you a reference, the normal range of load factors for commercial transport passenger transport aircraft is typically from -1 up to 2.5. The aircraft has control surfaces. We have 2 horizontal tails, which are all movable. Then we have 2 vertical tails sitting on the fuselage with conventional rudders. And then we have ailerons here along the trailing edges of the wing. Not right now. Can we make that move again? Okay, I will continue like that. So in the following, I'm going to show you the setup of our aeroelastic modeling process. Then I will show a comparison between CFD and aerodynamic panel methods, which are still very popular for a preliminary design of aircraft, which is also often justified. And
yeah, sorry, I'm trying to get the dock out of your way.
Perfect, thank you. And then I will continue with showing a maneuver loads analysis of that aircraft, covering maneuver load cases across the whole flight envelope. We start the design process with our software Modgen, which we use to set up, for example, the geometrical model. One of the many outputs of that software, shown here in green, is the outer geometry of that aircraft, which is more or less the baseline also for the meshing in CFD. And then for this in blue, you can see a layout of the internal structure of that aircraft in terms of primary structure. So for example, the spars and ribs, and also the position and number of the ribs. And together with the upper and the lower skin, this will make our structural model of that aircraft, which I realized in Nastran. So we have an FE model consisting mainly out of shell elements, plus some beam elements for stiffening of spars and ribs and this upper and lower skin. And what is important to understand here is that this is an FE model for aeroelastic purposes. So our goal is to capture the overall structural dynamic behavior of such an aircraft. So for example, first wing bending frequency. So this is not a structural model which you could use, for example, for a strength analysis or the sizing of some local component. To do that, the FE model would need to be much finer to resolve local stress peaks. So this is an FE model which is adequate for aeroelastic analysis. Speaking of structural dynamic analysis, also the mass modeling is important. So for us, it's not only the overall mass of the aircraft, which is important, but also the mass distribution over the wing, for example. What we do is we model the fuel mass distribution by modeling the different fuel tanks of the aircraft. Then we have estimates for the for the aircraft systems from the preliminary design, and we can derive the structural mass from the FE model based on material thickness and density from the FE model we've seen on the previous slide. And finally, we've got a payload. And from that, I made up 4 different mass cases to cover more or less all the different phases of flight of that aircraft, starting at the maximum takeoff mass with full fuel and payload. Then we have the basic flight design mass, which is an important load case for such an aircraft, because at that mass case, it has to achieve its full performance. Then we have another Mars case, but without payload, and then this is more or less operational empty Mars. The next ingredient for the aeroelastic modeling is then the aerodynamic models. As I said at the beginning, in the preliminary design, you often rely on aerodynamic panel methods, which in this case is the vortex lattice method for the subsonic regime and the Zona 51 method for the supersonic regime. And for the aerodynamic panel method, we discretize all lifting surfaces with so-called aerodynamic panels, which are shown here in the left picture. And they model the lifting surfaces as flat plates. However, you can apply a correction, for example, for the camber of the airfoil or the twist of the wing, which is indicated here in blue and red colors. Then on the right-hand side, we have the CFD mesh, which I set up using Centaur based on the geometry I created on the first slide. And this is an Euler mesh intended to be used for the CFD solver of DLR, the DLR tau code, and also for the SU2 Euler solver. Considering that this is an Euler mesh, it's already a pretty high resolution mesh, I would say, and I have a strong refinement here along the leading edge, which is necessary to trigger and to resolve the vortex-dominated flow, as we will see on the following slides. And because I intend to perform Euler simulations, there's no need of modeling a boundary layer, so I can then continue directly from the surface triangles with tetraeders to fill up the volume with some refinement here in proximity of the aircraft. Let's have a look at the features of the vortex-dominated flow of such an aircraft. What we can see here is a visualization of the vortices which occur using the so-called Q criterion, which is calculated for the volume solution. And then I used isosurfaces shown in blue color here at a given value of Q, in this case Q equals 450, to visualize the areas of rotation dominated flow. The operational point is a subsonic case with a Mach number of 0.4 and at an angle of attack of 15 degrees. And what we can see here is that we have basically two primary vortices, one starting here at the strake of the aircraft and then passing over the main wing and then going downstream. And then we have a second one starting here at the kink of the main wing, following more or less the leading edge and then going downstream. And in the center, we have an Euler solution prepared with a DLR solver tau. And on the right-hand side, we have another Euler solution prepared with SU2 code. And the good news is that the results more or less look similar. So the overall physical phenomena or the flow features are resolved in all three solutions, with the left one being the reference because it's a much finer CFD mesh which was used, and it's also a round simulation. So summing up, I would say that in the two Euler solutions, the vortices are slightly stronger, which is kind of as expected due to the missing viscous dissipation. The point is that these vortices have a significant influence on the surface pressure distribution of the aircraft in terms of suction peaks. I'm not so sure if you can see that well here on the beamer wall, but the suction peaks here are highlighted in greenish up to blue colors, here at the strake and here at the leading edge of the main wing. And again, the good news is that the surface pressure distributions in all three computations look very similar. So what I call the footprints of the vortices are captured, and this is here the key to success, I would say. Let's have a look at a small comparison with respect to the aerodynamic panel methods, which are shown here on the right-hand side, calculated with the vortex lattice method. What you can see are basically only two suction peaks at the leading edge here of the strake and then at the leading edge of the main wing, which is kind of expected again due to the potential theoretical aerodynamic approach of that method. However, I feel it's important to point that out because there has been some discussions on that. On the left-hand side, just for reference, you see what the solution should look like. I prepared that image by projecting the CFD solution onto the vortex lattice grid. So let's have some intermediate conclusions. The first point, we already just had that one. So the vortices are definitely not captured properly, neither by the vortex lasers method, and I haven't shown that, but also not by the Zona 51 method in the supersonic regime. Talking about the three different CFD solutions, from my perspective, I would say that Euler is a reasonable choice, at least for loads analysis, and especially when you think about the maturity of the aircraft design. Please don't understand me wrong. I'm fully aware that RANS has its place and purpose and is necessary for certain types of applications. So what does this mean for maneuver loads analysis? So first of all, we can say that aerodynamic panel methods are definitely at the physical limit here, and that for fighter configurations or any other configurations that have a vortex-dominated flow, we definitely should start using CFD as early as possible in the design stage. So why don't we do it right from the beginning? Well, the answer is pretty simple. It's numerically expensive and it's also labor intensive, because what we need for maneuver loads is not just calculating CL over alpha curve, but we need the fully trimmed aircraft coupled with FE model, including all the control surface deflections, and not just for a few selected operational points in the envelope, but covering the whole flight envelope. And in this case, it makes many, many load cases. So talking about the flight envelope, here on the left-hand side, you can see the altitude plotted over the Mach number, starting with the stall speed here in the blue curve on the left-hand side, and then up to the dive speed with the red curve on the right-hand side. And every dot on these curves marks one operational point, and in each operational point, a number of different maneuver load cases are calculated. What is a maneuver load case? For example, we have a horizontal level flight. That's easy. Then we have a pull-up maneuver or push-down maneuver, or we have roll with acceleration in opposite direction, sudden elevator deflections, and so on. And in some cases, also a combination of pull-up and roll maneuvers. So all these different maneuvers need to be calculated at the different altitudes for all the different mass configurations. However, not everything needs to be combined with everything. For example, at stall speed, there is no pull-up maneuver. However, doing all the combinations, I ended up with, in this case, 688 maneuver load cases, which I need to calculate, which are scattered across the whole envelope. And please remember that for industrial applications, for the certification of an aircraft, this is not very much. They have many more load cases than I have with my 4 load cases. So they do several thousands of load cases. So let's have a look at some results. When we talk about maneuver loads, I'm usually talking about wing root bending moments or torsional moments, so section loads. And we usually plot them in a 2-dimensional envelope, as shown here. For example, the torsional moment at the wing root plotted over the bending moment, because not only the single quantity is important, but also the combination of 2 quantities is typically sizing primary structure. On the left-hand side, I should say that all the different dots you can see here, each dot corresponds to one load case. So on the left-hand side, we have the results obtained with CFD, and on the right-hand side, just for reference, with aerodynamic panel methods. And on the first glance, the 2 plots look kind of similar, which is maybe due to because I selected the same color scheming. And actually, when you look at the scaling of the axis, they are more or less similar. However, there are some significant differences, which I'm going to point out in the following. For example, looking here at the top right corner, where we have the combination of maximum bending and torsional moment, we can see that the envelope is kind of dented or shifted to the left-hand side. Looking at the bottom right corner, we can see that in the aerodynamic panel methods, this corner is defined by all the supersonic load cases, while this is definitely not the case in a CFD. Actually, here we have subsonic load cases, and we actually do not have any supersonic load cases outside the subsonic envelope, so they are fully covered by the subsonic load cases. And finally, we can see for the aerodynamic panel methods, looking at the shape of the envelope and the orientation of the envelope, there is a rotation in clockwise direction of the supersonic load cases with respect to the subsonic load cases, which I cannot see in the CFD results. So summing up, there are significant qualitative differences in the loads here. So let's have a short discussion on my requirements on the CFD solver for such an application, because I think it's slightly different from what the typical aerodynamic specialist would like to see. So my first priority would be robustness. And this is because I have such a large number of load cases. Just to get you an idea, I handle them by running different simulations, so many individual simulations. And one maneuver load case typically takes 1 to 3 hours on 128 CPUs. So coming back to the large number of load cases, this also means that I need a high degree of automation, and there's definitely no room for user interaction. So I more or less have to run the simulations blind and trust the CFD solver. So I need to have a reliable solution, and that basically in all load cases, also those which are numerically difficult, in the sense that they are directly in the corner of the envelope or directly at the edge of the envelope, or maybe even beyond, depending on the demands of my trim algorithm. The second most important requirement for me is the Python interface, which Pedro showed some slides for yesterday. So the way my simulations work is that I set up co-simulation between SU2 and my own software, which is called LoadsKernel, which is also an open source software since a few months, and it is available on GitHub. And I do co-simulation. So the elastic part is handled by my software. I send over the deformations of the CFD surface to SU2. I set the operational point. I run the solver. And when the solver finished, I collect the results in terms of force vectors on the CFD surface. So let's have some conclusions. What I've shown you is a comprehensive maneuver load analysis covering the whole flight envelope of an aircraft, which is, I think, has not been published before in literature, neither for transport configurations nor for fighter configurations. What we found out on the way is that aerodynamic panel methods like vortex lattice or Zona 51 are definitely, well, not adequate for such an aircraft. So please forget them and use CFD as soon as possible here. If you're interested in more results, I have 2 publications on this work, one on the ICAS conference last year and one in the Aerospace Sciences and Technology Journal by Elsevier, which is published at the beginning of this year, and it's also open access, so you can download it and have a look at the results or just ask me. And for the requirements on the CFD solver, I mentioned robustness and the Python interface, but I want to add a third one, and that's definitely the support from the developers, because without that, this work would not have been possible. And before I conclude or finish my talk, I just want to give you a short preview of next work. And the video is not working. Great. Anyhow, thank you.
I'm curious, so you're doing deflections of control surfaces as well as deformations. So if you have that, you're using that deformation for everything?
Yes. No, I used mesh deformation for everything. Yes.
I is curiosity to develop comparing computational costs of
that's a difficult question. Not to answer, but from a political perspective. There are reasons why I went for SU2, and the answer is the robustness. So I don't know what the computation time of no solution would be. Yes, infinity.
Do I understand you automated the whole workflow through CPACs? You said that you extract from sort of database, generate models, or that was one.
We started in, well, I think at DLR and most of the aircraft design community, at least in Germany, uses a CPACs file format, which is short for Common Language for Aircraft Design. and its definition of aircraft parameters. This is where we just took the preliminary design from. So after that slide, everything goes a different direction.
That's another good question to me. So you need, well, someone in the Institute for Aerodynamics did the runs for different configurations you did on the oil level. You get access to the runs mesh types like in the Institute, you can shot with maybe
I have the access. I've seen the mesh, and I decided that I'm never going to use it because it was so large.
Okay.
It had 120 million cells. So already plotting already preparing these plots took a while. So I wouldn't want to run it. If they like big meshes, okay.
Are you simulating the again? Did you use it as like a constant or was it like more random?
I haven't simulated them yet. Well, I started with the help of Pedro at the beginning of this year, and first results are already available. I'm going to show some of them at the ECAS conference this year and the EFAS, the Aerolastic conference in the Netherlands. What I'm going to do is I have 1 - cosine gusts as specified in the certification specifications.
Thank you very much.
Okay, thank you.